10.4 is going to continue our study of logs, and we're going to talk about the common log. And really, the common log is base 10. So when there is not an index number written there, it is base 10. And base 10 is what your calculators will do. If you have something other than base 10, you cannot use your calculator. So this is kind of like when we take the square root, we don't put an index number here because it's the most common one we use. Just like base 10 is the most common, don't need the index number. As soon as we do something different, like a cube root, we need the index number. As soon as we do something different, like log base 5, we need the index number. So that's just something to look at. So simplest form, evaluate using your calculator. So log of 6. So really we're talking about log base 10 of 6. And I think it's really helpful to think about, what does this mean? This means 10 to some power is 6. When you think about what that means, it helps you think about what is the reasonable answer I should be getting. If I'm taking 10 and I'm trying to make it a smaller number, that means that my exponent has to be less than 0. So I kind of have a range or an expectation of what my answer should be, so I'm good making sure that I have a reasonable answer. If my number is something bigger, like 1,000, I know that my exponent is going to be a number greater than 1. So going to your calculator, all calculators are a little different. In this case, if we have log of 6, oops, clear this button right here, log of 6 is my log base 10. We hit enter, and log base 10 is 0.778 right here. And that's all it is to it. And you just need to play with your calculator to make sure that you know how your calculator needs numbers to be entered. So log base 6 in our calculators is 0.0778. And you really should carry 3 or 4 decimal places. If I go to what is the log base 10 of 0.35 and I go to my calculator, I get negative 0.456. Again, I'm saying 10 to what power is going to be 0.35. Since my answer over here is a number less than 1, that means I'm making some sort of a fraction, which is why it's negative. So I'm thinking about what should my answers be like. So in order to solve things that have that x in the variable position, if I have one term equal to another term, I can go ahead and turn this into the log. So remember, we can always move between log and exponent forms. So since I have term equals term, let's go ahead and rewrite this as a log. So we're still using our same formula we've been using since 10.2, so we really are talking about log base 5 of 62 equaling to x. That's great, but I can't calculate log base 5 of x. So what I'm going to, this didn't help. It's true, but not helpful. Because it's a base other than 5. So let's try something different. Let's take the log of both sides. We're going to take log base 10 of both sides. Golden rule of algebra is in play. What I do to one side, I have to do to the other. So I'm looking at the log of 5 to the x will be equal to the log of 62. Now, in 10.3, we learned a property that lets us handle the exponent with the log. So I know that this becomes x log of 5 is equal to the log of 62. Now the log of 5 and the log of 62 are numbers, and so I can use my algebra skills to divide both sides by the log of 5. I can go to my calculator, take log 62 divided by log 5, so clear. I have log of 62, clear, log of 62 divided by log 5, and my answer is 2.564. And so being able to take the log base 10 of both sides allowed me to go to my calculator. So again, we could rewrite 3 to the x equals 17 as a log base 3 problem. Again, log base 3 isn't going to help us, so let's go ahead and take the log of both sides. It's very much like, multiplying both sides by a number, dividing both sides by a number. It's an operation I'm doing to both sides. Apply that exponent rule. X is being multiplied to the log base 3, whatever that number is. So I'm going to divide both sides by log base 3, or log of 3. Those cancel. X is, when you go to your calculator, 2.58. Nothing really changes if I have an inequality. I can go ahead and take the log of both sides. So I'm going to have the log of 5 to the 3x is less than the log of 10 to the x minus 2. Go ahead and apply the exponent rule. So I have 3x log base 5 is less than, keep your parentheses, this is a single number, log of 10. Now, we have some actual numbers going on here. So we can go ahead and evaluate this number and this number. So go to your calculator, and what you see is that 3x, the log of 5 is 0.699. That is still less than x minus 2 times log base 10 of 10. That's one of our properties. Remember, that equals 1. So times 1 here, which really means times nothing. So I am still combining like terms, so I have a coefficient 3 and I have a constant term there. So I have 2.097x is less than x minus 2. I'm going to subtract x from both sides. So I have 1.097x is less than negative 2. Divide both sides by 1.097. And what I have is that x is less than negative 0.1823. So once you apply the log to both sides, you're really back to solving a basic algebra type problem. If we go ahead and look at this example over here, we're going to see a lot of the same strategies being applied. So we are going to do the log of both sides. Now remember, this exponent up here is a single number and you need to treat it as such. Go ahead and apply the exponent rule, which gives me log 7x times log of 2 is greater than 5x minus 3 times the log of 3. Now this time, this is a value and that is the value. I didn't get lucky enough to have log base 10 of 10. And so when I go to my calculator, I'm going to take 7 times log base 2 and I'll get 2.107 times x is greater than, and in this case log base 3, log base 10 of 3, log of 3 is 0.477. So I have 5x minus 3 is times 0.477. Then I have a distributive property going on there. And so I have 2.107x is greater than 2.385x minus 1.431. Get your x's together, so I'm going to subtract 2.385x from both sides, and I have negative 0.28x is greater than negative 1.431. Divide both sides by negative 0.28, and x, when I divide by a negative, sign has to flip, is less than 5.11. And so that is your answer. Now we talked about change of base. And so what happens when you have an expression particularly? If you have an equality, you can take the log base 10 of both sides and you're good. But if you just have an expression, you can't do that because you can't keep it balanced. You can't change the value by just randomly changing the base. So we have a formula. So this is a formula I would make sure to have on my cheat sheet. And it says log base a of n. If I want to go to base 10, really if I want to go to any base, but for calculators, if I want to go to base 10, I take log base b of n, the original number, divided by log base b of a, old base. I think it's easiest to see in this example. If my original problem is log base 5 of 12, and I want to go to log base 10, I take log base 10 of 12 in the numerator, and I divide that by log base 10 of 5, which was the old base. And that will give me the answer. So if I have log base 2 of 20, and I want to change that to something I can handle and manipulate, all I have to do is take the log of 20 divided by the log of 2. So this one becomes the numerator, this one becomes the denominator, and I've changed it to log base 10. I could change it to log base 5, I could change it to log base 7. None of that helps me at this level. I want to go to log base 10. And when you go to your calculator then, you get 4.3219. In the same way here, if I take the log of 18 and I divide it by the log of 3, that is equivalent to this, but now it is in log base 10, so I can use my calculator and end up with 2.6309. If you want to check your answer, remember what this means. This means that 3 to the 2.6309 power will equal 18. Let's go to our calculator quick and clear. If I have 3 to the, where's my new calculator? I don't see my power. To the 2.6309, I get basically 18 with some rounding error. So that is how you can check and guarantee that what you're doing is in fact still mathematically correct. And that is the end of the 10.4 lesson.